small announcement. All right, I'm just reminding everyone, sorry there. I'm just reminding everyone that the sign up for the September classes has started. So it's a real simple procedure. If you want to join in September, you just have your parents WhatsApp us. And of course, I will send them the registration form and prices, everything that they need, and they will make a decision, if they want to sign on for September or not. Okay? But let's continue from where we left off last week. So I told you all last week that we were going to start a brand new topic. And today it's the digestive system. How much of you all have done, I'm not asking if you did the whole of the digestive system in school, but if you actually did a little piece of it at least, let me know on the chat. Okay, so the digestive system, let me summarize this for you. You eat food or intake food, and of course, you need food to live, because food is what provides you with things like energy, protein, like to build muscles, of course, even vitamins and minerals, you need it. So when you eat food, your body needs to take that food and break it down into smaller pieces. And it gets smaller and smaller and smaller. And then it would get so small, right? Your body will be able to absorb all the necessary stuff from the food. And of course, not everything in food can be absorbed into the body. What cannot be absorbed or utilized by the body will be your body will need to get rid of it. Okay, and we will go through all of that. But on the screen is a summary of the process. So let's go through the real basic summary here. The flow chart is going like this. It's going across, then down, and then across, because I couldn't get the whole thing to fit in one line. So let's start off with the beginning here. One, we eat food, right? So we basically take food and put it in our bodies. Afterwards, your body will break down the food into smaller pieces. That part where your body is breaking it down into smaller pieces, that is what we usually refer to as digestion, when your body is attempting to break down food. But digestion is just one small part of a larger process. So after your body breaks down everything into smaller pieces, the smaller pieces, the useful pieces, will be absorbed into your blood, right? Believe it or not, all those useful things that your body needs, like glucose, proteins, vitamins, minerals, it will be absorbed into your blood. And guess what happens? All of those useful things will be taken to your cells, because it's your cells that's going to utilize and do great things with all of these smaller absorbed pieces. And I have it here in the blue part here. The cell makes use of these smaller pieces. And last, right, whatever your body cannot use, that's the thing in purple, it gets egested, better known as going to the toilet. Okay, so what I need for you all to do is draw this little flow chart over here and let me know when you are finished. Right, so we have a little breakdown of the digestive system here, or seeing that the digestive system, it's part of a bigger system. So here we have some, well, fun looking diagrams here. Remember I told you that when you eat stuff, you're basically trying to break down the food into smaller parts, right? And you want to extract the useful parts. So let's start talking about what is useful in food, right? What is useful? Now, there are many things that are useful in food. First of all, you're going to see some words that you're very familiar with here. One of them is carbohydrates. We all know we need carbohydrates, but why do we need carbohydrates? Carbohydrates are really, really good for energy. If you don't eat foods that are rich in carbohydrates throughout the day, you're going to feel very, very weak, which is obviously not a pleasant feeling. I want to see how much of you all remember this. I'm using the word energy, right? What is the name of the process, the biological name of the process by which your body creates energy? What's the name of that process? It starts with the letter R. Right, Saeed, correct. Amanda, correct. Kadira, correct. Right, it's Anrisha, correct. It's respiration. So here's what, right? Remember how your body creates energy, and with the respiration process, it would take glucose and mix it with oxygen. We're talking about aerobic respiration. And when you combine the two in the mitochondria, you get a lot of things, including what? Energy. But I now reminded you that for respiration to take place, for energy to be created, you need oxygen and glucose. But why am I talking about carbohydrates? Carbohydrates is not the same word as glucose. For energy, we need glucose, right? So let me tell you what happens. Let's say we eat a potato, right? Potatoes are a really, really good source of carbohydrates. What will happen? Your body will take that potato, right? So pretend you eat it and you swallow it, it goes down into your stomach, and then after your stomach, it goes into your intestines. It's going to break it down into smaller pieces. The carbohydrates usually gets broken down into smaller pieces, and these smaller pieces have names: glucose, maltose, and fructose. But more importantly, focus on the G word, which is glucose. So that is how we get glucose. Think of carbohydrates as Lego blocks. Everybody knows what Lego blocks is, right? Those little building blocks kids just play with, right? You could think of carbohydrates as a whole set of Lego blocks together, but your body will take apart those Lego blocks, and each smaller piece, each Lego block, has a separate name. Some of them are glucose, some of them are maltose, and some of them are fructose. The only one I am concerned about today is glucose. Maltose and fructose have uses in the human body. They have uses. It's just not on the CSEC syllabus. Okay, so let's talk about proteins now. Right, so foods that are usually rich in proteins are like meats, right? Like beef, chicken. Now there are vegetarian options to food, to protein, like tofu, but that's made, I think tofu is made from milk. But a lot of beans like peas and pigeon peas and dal and all of those things are rich in proteins. Now, just like how carbohydrates can be broken down into smaller pieces, guess what? Proteins, which are good for building muscles, your body will break it down into smaller parts. And those smaller parts are called amino acids. So in other words, proteins are made up of amino acids. If you take enough amino acids and you put them together, you will get something called a protein. All right. Now, just for general knowledge, right? Some people could actually go into a pharmacy and you could actually buy amino acids straight. Quick question, right? Which one will get absorbed into the body faster? Proteins or amino acids? Let's say Let's say somebody eats a piece of chicken and another person goes to the pharmacy and buys the amino acids just so. And he takes that, like he takes a spoonful of amino acids. Which one will be absorbed into the body faster? What do you all think? Joshua, correct. Sarias, correct, right? Percy, correct. If you said amino acids, you are correct, because check this out. The protein, if you eat a piece of chicken, first you have to eat that chicken. It have to go down into your stomach. Your stomach will begin to break it down. Then it have to go into your intestines. Your intestines are going to break it down even more. And only after all of that, then your body can absorb the amino acids. But if you take a spoonful of amino acid from the pharmacy, your body doesn't have anything to break down. It has no work to do. It will go straight into your stomach. Your stomach will pass it to your intestines. And believe it or not, your intestines is the one that absorbs everything into the blood. So if you take amino acids just so, you have less work. Your body has less work to do. Okay? Right. But the point is, proteins are made up of smaller things called amino acids. And let's get down to the last one, fats, which a lot of people think are bad. But like I said, too much fat is bad, but your body needs a certain amount of fat to be healthy. So foods that are usually good in fat, well, good fat are like cheese, and believe it or not, butter. A lot of people think butter is unhealthy. Too much butter is unhealthy. A little bit in moderation is actually very healthy, right? So things like cheese, right? When your body eats it, your body will try to break it down into smaller pieces. And these smaller pieces have two names: fatty acids and glycerol. Remember those two. In other words, if you take something called fatty acids and something called glycerol and you combine them and you put them together, you will get something called fats. Okay? Take down everything that's on the screen. Let me know when you are finished. All right, now I'm not going to ask anybody to draw this because nobody here is going to be able to draw this in time, right? But I urge you to take a screenshot, or you can just use the recording afterwards, right? The good news is, in the exam, no examiner is going to ask you to draw back these complex diagrams. The most you're going to have to do is just label pieces of the diagram that's already been drawn for you. So let's just go through the basics here. Just listen a little bit. You don't have to take down anything for the time. When you're eating food, obviously it goes into your mouth, right? I'm not going to give you a note on what your mouth is, right? I think everybody has a fairly good idea, right? And then when you eat the food, it goes down into a tube, right? Now, the name of this tube that connects to your stomach, and you can clearly see your stomach here, is the esophagus. Different textbooks just spell it different because it have the American spelling and it have the British spelling. So instead of an E, some books will have the letter O, right? I believe, I'll see if I can correct myself later. I kind of rush this one. I believe the one with the E, right, is the British spelling, right? So the point is, the food will go down the esophagus, right? Now we're going to discuss, well, let me discuss it one time. A lot of people think that when you chew and swallow food, it is fall down into your stomach. Do you think that term is correct? Do you think gravity is responsible for getting the food to fall down the esophagus into the stomach? What do you all think? The answer is no, right? And we could all eat upside down. If you hang upside down, like on a tree branch, which I don't advise you to, couldn't you possibly eat food upside down? You could still swallow food. So that means it's not falling into your stomach. What actually happens is that the esophagus has muscles in it. and the muscles contract and relax, contract and relax. And the muscles just actually push the food towards the stomach, right? I did not know that until I left high school. I'm not lying to you, but I didn't do biology in high school, right? I did technical drawing instead, right? And it's only after I saw a documentary, then I understood there was the esophagus was a muscle and it was pushing the chewed food to the stomach. Now, here's the thing. That motion where the muscles push the food towards the stomach, it has a name, and it's called peristalsis. And I need you to at least take down this. Peristalsis is a series of wave-like muscle contractions, right, that move food through the digestive tract. So it's this kind of pushing motion, this contraction, expansion and contraction over here of the muscles, right? Well, I shouldn't use the word expansion because muscles cannot expand. I should say contractions and relaxing. Contractions and relaxing of the muscles that push the food towards the stomach. And the name of that motion, that technique that your body uses is called peristalsis. So everyone at least take down what peristalsis is, okay? And someone just corrected me. E is the American spelling. So that means the English spelling will be the one with the O. And we use the British standard of spelling. So let's talk about when the food reaches into your stomach. Which part of your body, well, sorry, first of all, I should have mentioned that when you put food into your mouth, right? You chew the food, and well, it provided that the food is solid. So chewing actually breaks up the food into smaller parts. So that's part of digestion, right? So some digestion happens in your mouth. Then the food goes down into your stomach. Tell me if this is true or false. When the food reaches in your stomach, most of the digestion happens in your stomach. How much of you think that statement is true, that your stomach does most of the digestion in your body? Right, some people, that's a trick question. Let me explain why. Most people, not everybody in the class, right, but a lot of people are saying that the stomach does most of the digestion. That's actually not true, Your stomach does not do most of the digestion in the body. In fact, I would go as far as to say that your stomach does the least amount of digestion in your body, which of course is mind-boggling because you know that food goes in your stomach, and I'm sure at some point in time, people have always told you that your stomach does the digestion, but that's not actually true. The stomach does some of the digestion, right? And of course, we're going to investigate exactly how much it does in a little while. But when the stomach is done with its part, it will send the partially digested food into the small intestines. It's actually your small intestines that does the majority of the digestion in the body. And a lot of people don't know that. And I didn't know that until I left high school. Okay? Like I said, I didn't do bio in high school. Okay? How much of you all are shocked by that? That it's not your stomach that does the majority of the digestion. It's actually your small intestines that did it. Now you know, right? Even though if you didn't know, now you know, right? All right. Now, your intestines are broken up into two categories, two major categories. It's either your small intestines or your large intestines. So you have to notice, when the food now comes out of your stomach, you notice it's connected to the orange part. But look at the diagram properly. The food, the first part of the intestines is the small intestines. After your small intestines, they do the majority of the digestion. They break down the food into smaller pieces. Inside your small intestines, within that structure, the necessary parts, the amino acids, the glucose, the maltose, the fructose, the fatty acids, they get absorbed into the bloodstream. The things that cannot be digested will be sent to the large intestines. And of course, your large intestines is the part that will take you to the toilet after. Okay? So quick question. Does your large intestines do any digestion? What do you all think? Right. The answer is no, right? Okay, let me say that back, right? Remember, right? All the food, right? The last piece of digestion happened in the small intestines, because in the small intestines, so much digestion occurs and all the necessary things that your body needs is absorbed within the small intestines. So the remainder of stuff that cannot be digested, cannot be digested, is sent to where afterwards? It's sent to the large intestine. So no digestion occurs within the large intestines. The large intestines is just a holding facility for things that could not be digested. And of course, that goes to the end of your body here, right? So it's almost like, I guess, and I'm not saying the large intestines is useless. It has some uses, right? But in terms of digestion, the large intestine does none of it, which is amazing, because I know if I ask someone, because of the name, large intestines, you would automatically think the word large intestine means it has a lot to do with digestion, and it's the total opposite. Okay? So throughout my explanations here for the rest of the day, you're going to be hearing me referring to the small intestines, the large intestines, the stomach, and also I just want to point out part of the body here that may not be obvious. You're seeing the large intestines here in green, right? You all see a kind of light green thing behind the stomach. Look at it properly. You're seeing that light green thing behind. The purple part is part of the large intestine. The green and all of that is the large intestines, right? Right. So you see this light green thing behind here? It's kind of hard to see. So I'll put a little arrow. That's your pancreas. Right? I'm going to be mentioning him also. The pancreas is behind the stomach, right? Kind of like it's just jammed up in between there, right? Also, you're going to be hearing me discuss something called the liver, and underneath the liver, it have a little sac here connected to the liver, right? You know, this blue part is connected to the liver, and then it flows into this little sac here. That is called your gallbladder, right? So just make a mental note of where all of those things are. If you want to take a screenshot, take one now. But like I said, you don't have to draw this diagram. Let me know when you're finished, right? Whether you just finished looking at it or you finished taking a screenshot. All right. So what we're going to do now it's break up the digestion process into two major categories. Now, keep in mind, once again, digestion is all about taking bigger pieces and breaking it down into smaller pieces. So the two categories are mechanical digestion and its counterpart is chemical digestion. Now, whenever you hear the word mechanical, I want you to think of physical force. Like if you take a hammer and you begin to hit something, that's mechanical work. Why are we calling it mechanical work? Because we are using force to mash up something or do work. So mechanical digestion is the physical breakdown of food. We're using force, right? Of breaking down substances into smaller particles to more efficiently undergo chemical digestion. So I will explain the last part of that sentence just now. But whenever you talk about mechanical digestion, that usually occurs in your mouth because your mouth has two important features, teeth and tongue. And your teeth and your tongue together, they create forces that can munch on the food, twist around the food, and break it down into smaller pieces. So your mouth is mainly responsible for mechanical digestion. Before the biology students pull me up, right? Within your mouth, a little bit of chemical digestion occurs, but I'm not going to discuss that as yet. I just want you to memorize that your mouth is mainly responsible for mechanical digestion. Now, another way of breaking down food is to use chemicals, right? Within the human body, there are a lot of chemicals, and chemicals can be thrown onto foods, and those chemicals can attack the food and break it down to even smaller pieces. So, chemical digestion, let's read it through. Chemical digestion uses acids and something called enzymes. We're going to talk a lot about enzymes to break down food into simpler nutrients so they can be absorbed into the body. What your body does, right? Before your body undergoes chemical digestion, mechanical digestion will break down the food into small pieces to prepare it for chemical digestion, right? So in other words, mechanical digestion is step one. After your body performs mechanical digestion, it will send it to a different part of the body, and then the chemicals will start to attack those smaller pieces and break it down into even smaller pieces. All right. So let me know when you're finished with both items on the screen. Right. So I wanted to talk about something called digestive enzymes. Remember, we saw the word enzymes, but its real name is digestive enzymes. Your body has many different types of enzymes. Since it's the digestive system, it's digestive enzymes we're going to talk about. Whenever you hear the word digestive enzymes, we are clearly talking about chemical digestion. Here's what everybody should know, Pac-Man, right? Pac-Man is that video game, right? I want you to think of enzymes as a type of Pac-Man. And what he will do, he will attack certain types of food, right? And he will break down the food into smaller pieces. But enzymes are very specific and picky. There are basically three categories of what? Enzymes. I color coded here. It have a blue one, it have a yellow one, and it have what? A kind of grayish or blackish one here, right? The three categories of enzymes are carbohydrates. You notice that word resembles the word carbohydrates, which is no coincidence. One called protease, which of no coincidence resembles the word protein. proteins and one called lipase. Whenever you hear the word lipase in biology, think fats, right? Another word for fats is lipids. A lot of people don't know that, right? So instead of saying the word fats, another word you can use is lipids. So whenever you hear lipase, you know that enzyme or those categories of enzymes have to do with fats. Here's the thing. Carbohydrates, right, is a certain type of enzyme, and he only attacks carbohydrates, which makes sense, right? If you take a piece of protein and you put carbohydrates in the same container as protein, the carbohydrates will just look at you blankly, and he will never, ever, ever attack the protein. That's how I want you to visualize it. He will only attack carbohydrates. And when he attacks the carbohydrates, he will break it down into smaller pieces. And like I mentioned before, these smaller pieces could be things like fructose, maltose, but more importantly, glucose. Okay? There's another type of enzyme called protease. Protease will only attack protein. He will never attack carbohydrates. And when he attacks the proteins, he will break it down into smaller pieces, better known as amino acids. And lipase, well, guess what? He attacks fats. And of course, he will break down the fats into smaller pieces, better known as fatty acids and glycerol. And lipase, I know I'm saying it over and over, will only attack fats. If you put lipase in a container with protein, once again, he will just look at you blankly and do nothing, right? So let me know when you finish with everything on the screen. All right, so we're talking about acids. Now, this is a little sidetrack here, right? Here's it, hot and cold. When we hear hot and cold, we normally think opposites, right? I think that's a fair thing to conclusion to come to. When something is too hot, it can cause damage. We all know this. Hot things can burn you. But are cold things dangerous? Well, what do you all think? Can cold things also be dangerous? Can cold things kill you? Can cold things damage you? Yes, right? Cold things can damage you. A person can freeze to death, right? Or obviously, and if a person is out in the cold too long, they can get frostbite, right? And that's damaging. The point is, hot things are not the only things that can do damage. Something on the other side of the spectrum, which is cold, can also do damage. Let's bring that same mindset now into acids. Now, I already mentioned that acids from my descriptions, right, can do damage. If you throw acid on a piece of metal, it can burn through the metal. If the acid is strong enough and you throw it on somebody, it can burn through their skin, right? But what's the opposite of an acid? The opposite of an acid is something called alkaline or basic. For simplicity's sake, let's just consider alkaline and the word basic to be the same thing. Now, I know there's a slight difference between alkaline and basic, but the point is acidic and alkaline are opposites. So tell me something. If acids can do great damage provided that it's strong enough, do you all think alkaline things, which are the opposite of acids, do you think that they can do damage if they are strong enough? The answer is yes. And a lot of people don't know that. You see, it's because of basically movies, right? Whenever acid falls on something, it is do damage. So people get the idea that only acids can do great damage. And of course, the opposite of acids, people for some reason think it's good that alkaline stuff cannot do any damage. But believe me, if an alkaline is strong enough and you throw that on somebody, it will do great damage. It will burn them and whatnot, right? The point is, I'm making, why am I discussing acidic stuff and alkaline stuff? Within your body, pieces of your, certain sections of your body is acidic and certain sections of your body is alkaline, okay? It's very, very important to know which parts of your body are deemed acidic and which parts are deemed alkaline. Here's why. Remember this thing called enzymes? Different enzymes, there are many different types of enzymes. Certain enzymes can live in acids. It needs acids to live in. And certain types of enzymes can only live in alkaline places. So their structure was made to live in alkaline places. So if you take an alkaline enzyme and you put him in an acidic environment, he will not live. That enzyme will die. Okay? So the topic of acids and alkalines, right, are a separate topic in HSB and integrated science. But I just wanted to give you an idea, right? How do we measure if something is acidic or if something is alkaline? Because in almost anything in life, we can measure it, like temperature. To measure temperature, we could use degrees Celsius, we could use Fahrenheit. To measure how heavy something is, and we could use grams or kilograms. We have a metric to measure it. But how do you measure if something is acidic or if something is alkaline, and even more in depth, how acidic is something? How alkaline is something? To do that, scientists have come up with something called a pH scale. You don't have to worry what the words P and H stand for. All you have to know is this. Your pH scale starts at 0 and it ends at where? 14. There are no other numbers. There's nothing greater than 14. There's nothing less than 0 on the pH scale. 7 is directly in the middle, because half of 14 is what? 7. If something has a pH value of 7, it is considered neutral, right? Neutral means it's not acidic and it's not alkaline. It doesn't fall into any of the categories, okay? Distilled water, in other words, pure water is our benchmark for something that's neutral. Distilled water is not acidic and it is not alkaline. Anything greater than 7, so anything that's 8, 9, 10, all the way up to 14 is considered alkaline. Now, the more you go up this way, the stronger the alkaline is. So seawater, baking soda, milk of magnesia, ammonia acid, soapy water, and bleach, all of those things are alkaline. Out of all of them, which one is the strongest one on the list? Is it seawater? Is it milk of magnesia? Which one is the strongest alkaline there? Right, as you go up. So he is the strong, well, on this chart, right, it have other things like drain cleaners. You know, those things people just throw in drains to clean it. That's actually not acidic, eh? That's a really, really, really strong alkaline. And it is burn away all the, well, dirty looking stuff on the drain. So this is the strongest alkaline on my chart today. Might have higher things like I said, drain cleaners and whatnot. Anything below 7 is considered acidic. So if I come and tell you something has a pH value of 4 because it's less than 7, it's considered acidic. Okay? As you get lower, as the number gets smaller below 7, it becomes what? Stronger. So things like coffee and tomato juice, all of those things are acidic but they're not very, very acidic because they're close to 7. As the number gets smaller, like gastric juice and lemon juice, you see how those have very low pH values? Those are strong, well, considered to be strong acids. And gastric juice, you're probably wondering, what is gastric juice? Gastric juice is the acid in your stomach. And you can see it very low down on the pH table, which means gastric juice is one of the strongest acids out there, and it's inside of you. I find that's amazing. Right? I want everyone to take down the pH scale, right? Just know it goes from 0 to 14. Exactly in the 7 is neutral, right? And I think this is fairly simple to understand. And of course, according to the CSEC syllabus, you need to know some examples of strong alkalines, fairly weak alkalines. You need to know some examples of strong acids and fairly weak acids. Okay. All right. So let's see what's next on the list there. All right. So as predicted, right, we will we have a diagram here that deals with the different parts of the body, right? And which part of the body has, certain types of enzymes and whatnot. You're not going to have to draw the diagram in the middle, right? Most likely, all you're going to have to do is eventually take down everything in the colored boxes. But let me talk about it first, right? And then you can take it down. So let's start with the mouth. What do you need to know about the mouth? Your mouth is an alkaline environment. Your mouth itself is not an acidic environment. In other words, the pH value of your mouth, right, that area of your body, has to be above 7. In your mouth, you have saliva, better known as, well, you always call it spit, right? But the real word is saliva. Inside your mouth, the type or the category of enzymes found is carbohydrates. So quick question, since your mouth has some enzymes in it and it's carbohydrates, can your mouth break down proteins? What do you all think? If you left tofu in your mouth, like pure tofu, which is high in protein, and you just left it in your mouth, will it be able to break down the protein? No, correct. Because carbohydrates can only break down carbohydrates. Now, whenever you all get a chance, right? If you don't believe me, right? If you take, I guess everyone here does eat what? I know there are plenty of vegetarians out there. But if you take, let's say, a piece, a hot dog, and you slice it into one of those small circles, and you take that slice and rest it in your mouth. Don't chew it, just leave it in your mouth. Nothing will happen because hot dogs, well, sausages have a lot of what? Protein in it. And the carbohydrates will not attack the protein. Hence, it will not break down that piece of sausage, slice of sausage in your mouth. But try this now. Take a piece of bread. Bread is made from flour, right? Take that piece of bread, put it in your mouth. Don't do anything. Just rest it in your mouth. Don't chew it. And then check back 5 minutes later. That piece of bread would be completely gone from your mouth, dissolved. I'm using the word, not very dissolved, but the saliva, which contains carbohydrates, will attack the flour because the flour has a lot of carbohydrates in it, and it will break it down. It will almost disappear from your mouth. And that is why it's okay to, if you have a baby, right? It's okay to break small slices, small pieces of bread, and you can feed the baby bread, even though the baby doesn't have teeth, because the saliva in the baby's mouth will break down the flour, the carbohydrates. So that's why it's safe, right? The name of the enzyme, right? Remember, the category of enzyme is called carbohydrates, but the actual name of the carbohydrates, the type of carbohydrates, is called salivary amylase, not amylase, right? Amylase, right? Don't be like me and be saying amylase, and people laugh at you behind your back, right? More than they normally do, probably. All right, so everyone take down the red block for me. Now, here's the thing. It should be no surprise by now that your stomach, right, after all the talking we just did, the stomach is the acidic region because it has what? That very, very strong acid. Just like how your mouth has saliva, and the saliva is a type of digestive juice. Within your stomach, there's another type of digestive juice, and its official name is gastric acid. Gastric acid is that very strong acid, and floating about in that very strong acid is a special type of protein, a special category of protein called protease. And the actual name of the protease, the type of protease, is something called pepsin. Okay? Now, here's the thing. Since your stomach, the only enzyme that lives in your stomach, the only category of enzyme in your stomach is protease. So, quick question. Can your stomach break down fats, and can it break down carbohydrates? Will your stomach even attempt to break down fats and carbohydrates? The answer is no, which is no surprise by now, because I just, never earlier in the discussion, I told you all that your stomach is not the superstar you thought he was. The stomach, when it comes to digestion, can only, and look at this, it can only break down proteins. Imagine that. The thing that you thought that did the most digestion, he can only break down proteins. And he has how you say, the name of that protein, sorry, the name of that enzyme which does the breaking down, his name is pepsin. All right. But the stomach does have a very, very, very important use. It has that hydrochloric acid. And remember, that hydrochloric acid is going to kill all the bacteria. In case you eat any bad food or anything, it's going to try its best to kill all that bad bacteria. So I guess he's kind of a superstar still. So take down everything in green. All right, so the next area we're going to talk about is something called the small intestine. You all know the small intestine. The small intestine is a hero. He's the hero of the digestive system. First of all, let me explain why he is the hero. Let's look at the enzyme categories. Look at the type of enzymes you find in the small intestine. You find carbohydrates, protease, and lipase. You find all three, which means your small intestines can break down proteins, carbohydrates, and fats. The name of the juice that contains all of these enzymes is called, well, I like these names, it makes sense, right? Intestinal juice, right? So the intestinal juice is a liquid that contains all of these enzymes. Pretend the enzymes are just floating about in this juice. And the small intestine is what? An alkaline environment. Okay? So the small intestine is the hero. Take down the orange. Let's move on to the blue area. All right. So here's the thing, right? That little piece of the that I had mentioned earlier that was behind the stomach. Remember, his name was the pancreas. Now, here's the thing, right? When you're eating, right? Does the food come in contact with your mouth? Yes. When the food goes down in your stomach, the food comes in contact with your stomach, right? You could say it physically touches the food, right? And after the stomach, it goes into your small intestines. So your small intestine actually physically comes into contact with the food. Tell me something. Does any food come in contact with the pancreas? Do you think any food is pushed into the pancreas? Well, what do you all think? Right, Sahana, correct? The answer is no. No food actually goes into your pancreas. And let me explain, well, the order of things. After the food goes into your small intestines, then whatever is left goes into your large intestines, and then it goes out your body. Nowhere in that sentence, right, you'll notice that any food goes to the pancreas. So what does the pancreas have to do with anything? Why is he even necessary when we're talking about the digestive system? Now, here's the thing. The pancreas has many uses, but one of the main uses is that it has a special juice, a special digestive juice. And of course, I love these names again because they make so much sense. It's called pancreatic juice. And here's the nice thing. The pancreatic juice produced in the pancreas has carbohydrates, protease, and lipase. So those enzymes could break down all three categories of food. But what's the use? I mean, it's not like any of the food is going into the pancreas. But what happens? The pancreas, it will make these enzymes, right? And it will transport them. There's a little tube, and it will deliver it to the small intestines. So in other words, it's kind of helping out the intestines. Now, don't get me wrong, right? The intestines has its own intestinal juice. The intestines can make some carbohydrates, some protease, and some lipase, but it cannot make all. That's how I want you to think about it. So guess who jumps in to help, like a best friend? He will look at the small intestines and say, hey, like you're having some problems making some carbohydrates, proteins, and lipase. You can't make all. Let me help you out a little bit. And he will make some of them, and he will send it to the small intestines to help out his best buddy. Okay? So that's the use of the pancreas. But I just wanted to clear up that no food actually reaches into the pancreas. The pancreas just sends his enzymes to the small intestines, his best buddy, his friend. Let me know when you are finished with the blue part. Right? Right? So moral of the story, don't sell your pancreas. All right, so here's the next thing now, right? How much time we have here? Right, so let's talk about this part now. Let's zoom in right? Let's zoom into the small intestines, right? So we're going to pretend that we are inside the small intestines. And of course, it have the food here. So the food, and this is the top of the intestine, this is the underneath of the intestine, and this is the passageway through the enzyme, through the small intestine sac. Now, here's the thing. Your small intestine is the final part of the digestion process. Remember, all the big parts of the food, all the proteins have been broken down into smaller parts. The smaller parts are called the amino acids. Of course, you're going to get smaller things also like glucose, and then you're also going to get smaller things like what? Fatty acids and what? Glycerol. I forgive the spelling there. All right. So remember, I told you, right, that when your body has finally broken down all of these things into smaller parts, where does it need to go after? All of these useful things, the amino acids, the glucose, the fatty acids and glycerol. Anybody remembers where it has to go right after? What do we do with it? It has to go where now? No, okay, let me pause it here. The answer is all of these useful things have to go into the blood. Remember, I said that at the beginning of class? All of the useful things has to get into your blood. And once it reaches into your blood will take it to all the cells, and your cells will make use of them. So the question is, how does it reach into your blood now? Because right now it's in your small intestines. Inside your small intestines, right, it have these little small finger-like projections, right? These small finger-like projections are called the villi, or sorry, villi, or villi, however you want to pronounce it. What will happen inside these things? It has small blood vessels. These small blood vessels, which one are the smallest blood vessels? Arteries, capillaries, or veins? Which ones are the smallest types of blood vessels? Do you all remember from last week? Which ones are the smallest ones? The capillaries, right? So inside these villi, or singular is villus, right? Inside of them, underneath them, it have these little capillaries. Look, I even have it here, the word capillaries. And what will happen? It have a real thin layer here, but the thin layer is not a problem because it's so thin, it's going to soak through all of these useful things. It's going to soak through this very thin layer in the villi. And once it soaks through, guess who waiting over here? The capillaries. And all of these useful things will seep into the capillaries. And once it reaches in the capillaries, well, great. The capillaries are connected to the what? The veins, it connected to the arteries. So eventually it reaches into the main blood stream. But there's a small catch, right? A lot of people don't know this, right? But you notice for the fatty acids, well, not notice, but those who are familiar with the topic, I'm not supposed to draw an arrow there. It's safe to say that the amino acids and the glucose will go into the what? Capillaries. The capillaries have blood in them. But the fatty acids and glycerol don't directly go into the capillaries. They go into a separate river, a separate channel, and that's called the lacteal. Now, this is a complex story, right? The fatty acids don't get mixed with the glucose and amino acids in your blood directly. it will go into a special structure called the lacteal. Now, for those who are doing biology, eventually this blue river will meet up with the red river. And eventually the two of them will mix, the amino acids, the glucose, and the fatty acids. But initially, right, at the beginning, there has been two separate channels, two separate rivers. Okay, and here's the thing. Once it goes into the blood, we're just talking about the glucose and the amino acids, just to make things simple. It has to go to the liver through a special vein called the hepatic portal vein. All right? So obviously things like the word hepatic portal vein and whatnot, right? But that's for a separate topic in integrated science, right? But here's what I want to clarify. Think about it from your perspective, right? Let me say you have a building, right? So you build this brand new building, and a whole set of new people now come in to the building, right? Right? Do you think you should search them? Do you think you should search them? What do you all think? I think we should search them. So this is a very similar scenario. Remember, your bloodstream come like this new building, right? And a whole set of new things are now entering the bloodstream. You don't know if all these things are good things. You don't know if all these things are bad things. Remember, fine, we know amino acids are good. We know glucose is good. But toxins, and somebody could ingest something toxic by mistake. And of course, it would get absorbed into the bloodstream. Also, too much amino acids not good. Too much glucose not good. I mean, glucose is good, but too much of anything is a bad thing. So your body will have to make a little security check. What it will do when it now enters the blood, instead of taking all of those things to the cells one time, they just take it to who first? Look at it. It has to go to who? Mr. Liver. I want you to think of your liver as a security guard. He's going to perform checks. He's going to check the amino acids. He's going to check the glucose, and he will decide whether or not it have too much amino acids coming in, if it have too much glucose, if it have toxins coming in. And only after he performs his check, then he will release it back into the bloodstream, and then it will go, hopefully, safety to all the cells. All right? Everyone understands everything there? Like, I have a good idea? Everything I basically just said here, it's in the green box and I don't know what color that's supposed to be, right? Take down everything on the screen and let me know when you are finished. Recording, right? For those who came late, the registration for September is on. So if you're interested, you just have your parents WhatsApp me, okay?